Hey, John, thank you for coming in again today. Just an outstanding history of contribution globally in so many different dimensions. I would say you're the only leader I know of that excels in every area. And every, it's quite remarkable to see that in one person, whether it's as an investor, a founder, a scientist, an educator, um, as a philanthropist with your in the world's largest sort of leadership scholarship at Stanford. I mean, across the board, it's just outstanding and amazing. So, again, thank you for sharing your insights now in our third interview.
Happy to do it. I just haven't been tested sufficiently, so that could be, or I deal with my failures well.
Just really simply remarkable. So let's do some updates. And for the audience, these interviews are always unscripted, so we're just going to get into a dialogue. There since our last conversation, we did this so while COVID was sort of launching globally, and you predicted that vaccines are going to be an amazing thing. You also indicated that all the work in AI machine learning was going to be a big factor and really uncovering and accelerating and helping impact in many positive ways. And we even talked about the microbiome in the gut and 3D chip architectures and so on. So I'm going to continue that conversation. You saw this rollout of GPT back in, I guess, fall of 2022, and you've seen it proliferate. What are your views on that, and where do you think it's going to continue to go?
So I think the most important insight from this is, all of these techniques, basically, the large language models, are basically natural language systems. That's fundamentally what they are. They've also memorized a lot of facts, but that's secondary. They're natural language systems. And the reason they seem so lifelike or human in their abilities is because language is deeply embedded in what makes humans unique. It really is it's our fundamental advantage. It's the way we not only communicate with one another, it's the way we organize collaboration, it's the way we share information. So language is so fundamental, which is why these systems that don't really have limited knowledge, limited semantic capability, actually seem so smart because they are quite good at natural language, right? But basically, what a large language model does is predict the next sequence from a starting sequence, right? And the fact that they're good at it is partly due to the fact that they've been trained on massive amounts of data, really massive amounts of data. And the scale of the model is equally large. The challenge we're going to face, I suspect, there are a number of them. We've made some progress on the hallucination problem, but that's primarily by human factors and human tuning of these systems. We'll continue to make progress on that. But the big challenge I think we're going to face is that the scale of the models is growing much faster than the improvements in underlying hardware technology that's used to train these models. So the cost of training and the scale of the machine that you need to train these models is going up at a very rapid rate. That is not sustainable. It's simply, especially not with the end of Moore's law and various other things, it's not sustainable. So we're going to have to find new improvements, algorithmic improvements, and improvements in the methods that we use for these systems.
Yeah, I mean, it's quite remarkable, right? And I mean, there's even talk of AGI, artificial general intelligence, not being something like 100 years away, but
Right.
next 10 years or less. And you saw Kurzweil come up with this new book, and he's even suggesting by 2029, amazing things are going to happen. I just did an interview recently this year with Vinod Khosla, and he was talking about sort of the penetration of robots and the implication of that. There are so many different ways that the large language models can enhance society. Do you see that being implemented in education in a profound way, perhaps in some areas of healthcare and other areas, and Stanford really being a leader globally in all of these domains?
Yeah, I think there are a number of areas where large language models or other recognition, whether say image recognition systems will be vital. Let's start with education. I mean, the real challenge we face in education is the difficulty that a teacher has in dealing with a classroom with 25 students in, let's say in math or science, where the students are spread across a wide spectrum of accomplishment. Some of them are ready to move quite fast. The middle group is the one the teacher typically will focus on because that's where most of the distribution is. But of course, the young people that are struggling probably need more time from the teacher. So this is a place where I believe we can make some progress on really building tutoring systems that are effective. In the past, the attempts to do computer tutoring have not worked very well, but that's because they haven't been trained by looking at how young people really learn. And I think we can make progress there. Sal Khan's working on this problem really hard. A number of other people, Carnegie Mellon, a number of other ed school people are working on it. So that's one good example. I think healthcare is another fantastic opportunity to really improve the effectiveness of nurses and doctors by, first of all, unburdening them from things they have to do. A doctor shouldn't waste time typing something into a system, right? They should speak to it, that a natural language system should interface and should record and update the patient record. Another area which I think people are experimenting with is being the interface between a doctor and the patient. And the problem is doctors are so pressed for time, and medical jargon, it goes right over the head of most people. Can you use an AI system to be the interface and use a natural language to explain and answer patient questions more effectively than tying up a physician or somebody else with it? So I think there are lots of good, and in image recognition, obviously, we've already seen a lot of progress in radiology, in reading angiograms, other things. So where the AI technology is better at looking at it, many images, partly because it's been trained much more extensively than any human could ever be trained, right? I can feed in 10,000 ground truths marked X-rays to a system and train on that. I can feed in 30,000, 40,000, which is what an X-ray technician might see in a lifetime. So I think there are real opportunities in healthcare. Healthcare and education are important because those are critical problems for our country. One, because it's too expensive. The other, because it's not working as well as we'd like. So by focusing our technology on those two, I think we really could do some significant improvements for the country.
You know, there's areas like interdisciplinary and transdisciplinary, and it seems to me that AI in general and machine learning and also large language models will be really good at finding sort of the patterns or the connections. And just this past week, there was this new language model released called AI Scientist. And it could do the ideation, it could actually do propose the research to be conducted, it can do reviews, it can even do the draft paper, and it has an automated review session. And they're applying it to machine learning and AI, and they're really curious. And they had external people evaluate it, and they're saying it's kind of like the papers would be okay for even top conferences. Though maybe a little bit weak, perhaps, but they would be even sort of available, or it could be used in top conferences. What do you think about that aspect of it? You know, science discovery, because it can amalgamate and show really all of this interdisciplinary aspects, right?
Yeah, I think there are clearly some problems that in scientific research where large language models are helpful. I mean, I think clearly improving people's writing and making things more clear and transparent in writing is clearly one, but also helping with other references and related work and determining that. The real question will be, when will we get to the point where AI has the initial germ of the idea that gets the breakthrough, right? That does what Jonas Salk did in creating a polio vaccine, right? Or Fleming did in recognizing the ability of penicillin. We're not quite there yet, but let's see what happens. I mean, these models that are trained in a particular domain really have deep domain knowledge, and that's the advantage they have. And I think we're going to see more and more. You may see a large language model as the interface to a system, but below that will be things that do specialized kinds of knowledge, do mathematics, do scientific reasoning, do other kinds of things, and are trained specifically in that domain, which will be beneficial.
Yeah, and then I'm kind of thinking there's this idea that these systems will then get into more sort of long-term planning, so they can work over a period of time. This idea of a context window, the ability to take a lot of information,
Large context.
yeah, yeah, in the millions.
It's amazing. It's absolutely amazing. I mean, take a really large context and use that. I mean, that's a phenomenal achievement.
Yeah, and then even spin off agents, right, on their
Yeah.
own.
Yeah.
To
Yeah.
handle sort of
Yeah, and you mentioned robotics. I mean, I think machine learning is probably one of the most important things that's happened to robotics in the last 20 or 30 years in terms of a better way to do planning and learning, right? Because robots, to some extent, robots need to be versatile and they need to learn. And how do we learn? We learn machine learning is the way we use that technique to learn.
You know, a couple of years ago, we talked about AlphaFold 2, but now it's AlphaFold version 3. And I'm just amazing, this ability to look how amino acids fold into proteins, but also show the association, like the interaction between DNA and RNA and proteins and ligands and so on. And that's just another dimension. I mean, these things are not possible really in classical techniques. What are your thoughts on that, where that's going to go?
Yeah, I think you're absolutely right. It's not possible in classical techniques. And I think what these AI-based systems have done, as in other areas of scientific discovery they're looking at. For example, there are people working on using machine learning to do turbulence, a problem that has frustrated people who want to do it from basic principles forever, because from basic principles, the computation is simply not very tractable. So I think what these systems are doing is they're using combinations. They still use simulation, but they use it in combination with an AI-driven system that really helps search a wider space than you could possibly ever search if you were doing it as a simulation from basic principles. And that's the real advantage. It doesn't guarantee that the system is going to come out with the optimal solution, but it probably tells you it's going to come out with a pretty good solution. And that's the big advantage in these problems, because otherwise, you know, if you have to do it fold a protein correctly from basic principles, I mean, the computation is phenomenal.
Yeah, I think the known protein sort of universe was like 250,000 3 years ago. Now it's like the 200, 300 million or
I know. That's just amazing.
Just incredible. And then applying just basically AI machine learning to things like fusion reactor design, right? And how that's going to go. And you could do these optimizations that weren't possible before. So, I mean, you could do hours just exploring that whole dimension. So I think it's really interesting where it's going. One of the things that you mentioned, though, was the underlying hardware. And in fact, I did 2 interviews with Philip Wong from your university, just all the work he's doing on semiconductors. And an IEEE Spectrum earlier this year, he did an article saying that maybe within the next decade, we'll hit 1 million or 1 trillion transistors in a GPU using things like chip on wafers on silicon or system on integrated circuits and, you know, different and then 3D layering, which
3D layers.
Yeah, we talked about that even earlier, but that sort of area is just exploding. And I noticed on a chart in one of the IEEE Spectrum articles this year, he talked about a 1.73 time factor in the increase of transistor density over the next maybe doubling or increasing by that amount 1.37 times over 2 years. And then a 3x energy performance kind of efficiency factoring as well over 2 years. So there is some underlying work, right? You know, carbon nanotubes, 3D architecture. Do you think it's going to help, right, on the energy side and on the data center side?
Yeah, there's two pieces to this problem. One is, how do we stretch conventional silicon as far as possible, given the slowdown in Moore's law, issues with energy efficiency, and the answer to that is sort of multi-chip, 3D stacked kinds of things, probably using integrated circuit technology to allow extremely high density interconnects to be done. But we're already facing that problem already, and you see companies like AMD, for example, opting to move in the multi-chip module direction more aggressively than building larger chips, because larger chips are they're totally energy power limited, totally power limited. And the other problem is the most aggressive technologies out there for building logic, so arithmetic units and things like that, are not going to deliver comparable benefits for memories. So there's no reason to move the next generation memory DRAMs into some of these technologies, because you're not going to get any improvement. And so you get a cost increase without an improvement. So that sort of will be the next 10 years or so, my guess is. The real challenge after that is there a technology to replace silicon? Phillips worked on carbon nanotubes. There are a couple other thoughts out there. But that's that's a junction where one of two things is going to happen. Either we're going to make another breakthrough similar to the one that were originally made in the discovery of the transistor and then subsequently the integrated circuit, or hardware is going to stop getting cheaper. And hardware stops getting cheaper, then software people are going to have to worry a lot more about the efficiency of their code and how it runs and things of that form, which we've kind of not worried about because the hardware has gotten cheaper at such a dramatic rate.
Well, I saw this announcement early this year on CRAM, this computational RAM, right? Just sort of the integration of computation and RAM, and you have these ultra high bandwidth sort of integration that's occurring. So, what are your thoughts on that sort of improvements in RAM technology? Right?
Yeah, so there've been a number of people who've done. There's CRAM, there's processor and memory is another way to think about it. The difficulty is going to be the divergence in the technology. So DRAM in particular is a very specialized technology, right? And it uses a unique structure that isn't going to be the way in which it's very different than the way you do logic structure. And of course, there's noise sensitivity as well. I mean, if you're doing arithmetic circuits and you're doing a lot of input or output, then you've got noise immunity issues you have to worry about as well. So I think we're going to have to, we're going to go through a transition, the next generation technology. For the first time in history, the cost of an SRAM, 1 bit of static memory, will not be cheaper in the new technology than it's been in the existing technology. And we've been on this curve that's gone like this. All of a sudden, it's going to flatten. And that's a dramatic change. It just means all these assumptions we were making when we did designs going back over decades are all of a sudden going to change. And that's going to cause initially some small changes in the architecture, but over time they'll build up as these trends continue. So I think that's why, despite the fact that Moore's law may be coming to an end, the challenge for both hardware and software designers is not going away. It's going to get more challenging, if anything.
It's interesting. I've been serving on the investment committees for the Canadian government where we're doing fund of funds, venture capital, private equity. I can't talk too much about it because it's sort of yet NDA, but they have done some public announcements. And in addition to that, the government has set up superclusters in different areas, which are really important to maintain leadership. And the Canadian government works closely with the American government. We also have a direct investment fund called the DTech Fund. In fact, I'm talking to the head of the fund shortly, and I interviewed him, wrote a Forbes article with him or on him on the interview. But there's this whole area of photonics, and the Canadian government has invested in quantum photonics, but photonics in general. do you think that's going to be part of the solution in chip technologies? Not looking at the quantum side, but just in chip technologies in general.
Yeah. So if you see what's happened over, let's say, the last 20 years, 30 years in photonics, if you go back 20 and 30 years ago, it was used only for really long transmission, right? Cross country, things like that. We were using fiber for that. Then now your home connection, my home connection is fiber, right? So now I'm using fiber at the home connection. Inside these large data centers, it's been now used, first it was used cabinet to cabinet connection. Then it was used board to board connection. And as the technology gets more integrated, the real challenge is you've got to integrate the technology that does photonics well, which is different than base silicon technology, with the silicon technology. And if you can make that interface very efficient, then you can move photonics closer and closer to being a chip to chip, or maybe a module to module interconnect. So imagine that in the future, you've got a module that's, say, this big, that's got 50 chips on it, mounted and connected at very high density with something that's similar to the on-chip interconnect. And then that module connects to an adjacent module, which will be right next to it with photonics, in order to get real high bandwidth up. And the place photonics really wins is where you've got physical space limitations. So you can't have thousands of conventional metal lines connecting two modules or two chips, for example. And there you can get real advantage in photonics. That will justify the conversion between electronics and photonics, that justifies that energy cost of that conversion. So I think we'll see it continue to move closer and closer to chip to chip. If somebody really builds a hybrid technology that puts the two together really tight, then that will make it even easier to do.
One of the interesting things in my dialogue with Philip, and then I saw the IEEE Spectrum article this year, is people don't realize the importance of chips, because it's really the basis of powering everything out there, right? And I guess one of the areas that's a concern then is the talent shortage, especially in chips, because a lot of graduate students are really attracted to the AI side or some of the other more the ones that are getting the spotlight, and there's a talent shortage in the chip area. So how is that going to be addressed? Because really chips are driving it all, right?
Yeah. I think it's about rejuvenating the excitement about silicon and its key role in driving the entire industry. But you're absolutely right that everybody wants to do AI these days. They all want to do AI, and there's a mad rush into computer science and AI. And the area of semiconductors, the area that Philip certainly works in, and lots of other people at Stanford have worked in over time, there isn't sufficient manpower. Without that kind of without both the research capability as well as the ability to implement and design, you will not be competitive in this. And those AI dreams will all begin to wane as we can't make progress in the hardware. But you're right about chips. I mean, I think we certainly saw this in the pandemic, right? I mean, the supply chain problems in chips not only affected the computer industry, it affected the car industry, the consumer electronics industry, the home appliance industry. I mean, you don't build a car has more than 1,000 chips in it now. So you basically, everything that's modern is covered with silicon, right? And as we learned in the pandemic, technology with things like Zoom and other things could get us through a lot of challenges that existed in the pandemic. But of course, it all depended on the underlying semiconductor technology to power that.
Well, I thought Philip's article, though, this year, which he authored with other researchers, I thought it was pretty positive. He thinks, or my impression is, he thinks chip technology can keep up, right?
Yeah, I think it'll be. I mean, I think it'll be if you look at Moore's law and there's all this talk about the end of Moore's law and things like that. If you look at the curves, so Moore's law was this exponential growth, right? So we've seen, from the early, let's say, the early Intel chips at that time, 1,000 transistors on a chip. Today, 1 billion transistors on a chip. So that's a gigantic improvement. Okay, we're off by maybe a factor of 25 to 50 from what Gordon predicted. But that means we're off 25 to 50 over, but we're a million times more dense than we were. So the million swamps the 25 to 50. And yeah, that 25 to 50 is going to get a little wider over time, and we're going to get more separation. But it's not going to instantly vanish. I think there are other issues which are more complicated than that we're going to face before we see a complete flattening of silicon.
Yeah, I mean, it's just fascinating, the whole chip industry, and Taiwan Semiconductor, of course, being the largest fab in the world, and they're setting up through the CHIPS Act support as well, a major investment in the U.S., which should happen, right? More investment in the U.S., and I think it's a good thing. And so those are some positive trends. And I guess really what was surprising to many people was NVIDIA, coming from this sort of niche market in gaming and then in GPUs and I guess Jeffrey Hinton and his team realizing that GPUs were something that could drive when they did the ImageNet competition, right? But really riding the wave where, if you look at their market capitalization, it's just really increased significantly. So I've been following Jensen and his work, and we'll see where that goes because there's competition, right? I mean, Google, Alphabet, you have your own chip technologies, Microsoft, AMD, and others. How do you think that's going to play out? Do you think it's going to kind of get balanced, because they do have their CUDA, right? And so much optimization is driven through their CUDA platform. It's, so what do you think it's going to happen? Do you think it's going to even out?
Well, I think there's lots going on here. I mean, there's both, first of all, the demand far exceeds the supply that any one company can provide. So there'll be multiple solutions. They're different in various ways. There are nuances, as well as a few companies that are emerging that may offer yet another solution, GraphCore and others that are out there that are trying to do some new approaches to the problem as well. Different than either the approach that, let's say, that Google uses in TPUs or the one that NVIDIA uses in the GPU family, in the computing family. But I think the key is that you had to break some things in the way we traditionally think about general purpose computing. So we had to move to SIMD structures, single instruction, multiple data, because they're much more efficient. And then, of course, the programming model has to match that. The traditional problem with SIMD computational models is that most programs won't run very well, right? So you take an arbitrary piece of C code and you throw it on top of the GPU, you're going to be very disappointed with the results. You're going to pay a lot of money and you're going to get lousy performance. So that's not the right way to use these things. I think CUDA was a big step forward because it provided a bridge so that programmers could be aware of the underlying structure of the GPU without having to wrestle with all the details of it. And that kind of interface is critical in the same way that TensorFlow plays it and other PyTorch and other ways of doing this. They bridge that gap, allowing programmers to specify things in ways that the hardware can implement much more efficiently. If you were just programming in random C, you'd be wasting your money. So that's the key, is that kind of hardware-software interface is critical.
I do all these keynotes all the time to CEOs and investors, and they're always curious about, should I be continuing to invest in programmers and coders? I get this every time. What is the future of work? Because of the rise of all of these technologies. So what are your views on that? Should people still become, software developers and take software engineering and things like that? Or?
Yeah, so my view at the sort of 10,000 foot level is AI is a human accelerator, a human booster. It is not a complete human replacement. Yeah, there are some jobs that will probably be completely replaced, right? Customer support function, which is terrible anyway. We would do better at doing that. translation functions. There are some things where I think we can do. But take the programmer. Really, things like Copilot and other tools really become ways to amplify the ability of a programmer and improve efficiency, just as other tools have improved efficiency over time, right? We change our programming structure, right? We move from C to C++ to things like Python to get improvements in programmer productivity. And things like Copilot and other AI assistants for coding will do the same thing. The reason I think we don't want to pull humans out of the loop is that we know that these systems can actually produce code that's got major flaws in it. The documented great paper that's been written that talks about security flaws and the ability of these systems, the frequency with which they introduce a security flaw, which is a major problem. And the difficulty, it's very easy. You give an assignment to Copilot, it writes a piece of code. It's very easy at that point to never really check it and see if it's right. And I think that's a really problematic thing. Now, it may be faster than writing the code yourself, but it doesn't mean you can't. You still have to go read that code and make sure you really believe it's right. In the same way that programmers do for one another when they check in pieces of code and they do code audits. So I think we're going to have programmers around for a while, and we're going to have most of these other functions. We're not going to replace doctors. We're going to make it more efficient for doctors to get their work done.
Yeah, I mean, it's just really, really fascinating. And I guess we're sort of alluding to this, right? Really, the reality is hybrid systems.
Yes, absolutely.
The mixture of all of these computing platforms available in the cloud, maybe some on premises as well, depending on what the security issues are or how much localization required. So in these hybrid systems, then you've got exascale computing capability, right? Where you can do a billion floating point operations per second. And when do you think we're going to set zettascale? That's a trillion billion in the supercomputing space.
It's a good question. I mean, I think it's probably driven as much by what the market demand is as it's driven by how quickly we can get there, because we're not going to get there in a way that's completely cost efficient. It's going to be a very large machine at that scale to get that kind of computational capability. Either that, or it's going to be a loose network of major data centers. But the problems they can collaborate on efficiently are somewhat limited, because really difficult problems have lots of interlocking pieces, which make it difficult to do that. And the other thing to keep in mind is there are two drivers, really. One is fundamental large-scale scientific simulation of really complex systems, right? Simulating a nuclear reactor, for example. The other is these ultra-large scale, large language models and their successors. But both of these, in the large language model, which seems to be the big driver right now, it's the training function that's really requires ultra-large scale machine. For inference, there may be a lot of demand. Inference may take more time than a traditional online search, for example, or something like that. But the key is that you've got millions and possibly billions of people doing inferences at once. So there, a different computational approach will work. You don't have to centralize the entire machine. You can distribute it, but you need lots of aggregate bandwidth, if not tightly interconnected bandwidth.
I mean, that's a really interesting. I mean, the national laboratories in the U.S. have now exascale supercomputers, right? And you can use them for medical discovery simulations. You can use it in a variety of different applications. And there'll be a driver to do zettascale, and just kind of the natural evolution, because there's competition, right? Globally.
Right. There's global competition.
Yeah.
Going to the moon.
or to Mars, maybe.
Or to Mars.
So, I mean, I've been following that space. Do you think that analog computing, which was an old idea, and now it's getting more attention, and do you think analog computing is going to get even more penetration?
Yeah, so there are a bunch of ideas, analog, neuromorphic kinds of ideas, things out there. So the advantage of analog, the advantage is you can get more potentially more density out of a device than doing it digitally. The problem is that precision and other things, the advantage that the digital world has, particularly in integrated circuits, is the devices are nonlinear. They're on or they're off. There's no in the middle. And that leads to tremendously high reliability, right? Transistors, the reliability of transistors is phenomenal. And this is one of the problems that people working on quantum, their reliability is off by comparison to conventional transistors by 6 to 9 orders of magnitude. That's incredible. So when you move to the analog world, you lose that advantage that a transistor is this simple switch on or off, boom, boom, boom. And that's what makes analog more difficult. So if you look at the long-term trend, analog's been wiped out over time. I mean, even for things which, let's say, in the 1980s, analog was doing, which some things in the RF space and various other things, signal processing kinds of in the analog world, that's gone. That's gone. It's been totally replaced by digital. So, we'll see what happens if if a new technology were to come along, which was more amenable to doing analog, you might go back and look at that again.
Yeah, I mean, I looked at a paper back from '92 on super Turing, and sort of has this analog ideas embedded in it, and it looks really interesting. And there's been some researchers who have built sort of discrete hardware to kind of illustrate what is possible. It'd be interesting if you can condense that into a chip form. You mean using gallium arsenide or something like that, right? So it's an interesting area, and maybe hybrid systems will be some kind of combination.
Yeah, it may be. It may be. I mean, the natural world is analog, but the first thing that happens is we convert everything to digital, and we do all the operations in digital. But maybe in the future, you'll do more processing in the analog space before you move to the digital space.
And I guess there's this whole excitement over quantum. And I remember back in 2015, I was asked by a group of CEOs of financial services to look 10 years into the future. And I said, you got to look at quantum, and their component were saying, man, that's like 100 years off. And I said, you wanted me to tell you what to look at 10 years in the future. You better start looking at it now. And it's taken off, right? And if you talk to most quantum researchers now, they're not saying 2100. They're saying in the next 10, 15 years, we'll probably have some kind of universal quantum system, and even discrete sort of narrow applications rolling out within the next few years. I just did an interview with the CEO of Quantinuum, and they just had a number of announcements this year, right? Where they got 3 nines fidelity, they're going for 4 nines, and he's sort of alluding that maybe 3 to 4 years, we're going to have something really practical where it's better than classical. And then you had their joint announcement with Microsoft, right? Where again, they're kind of a breakthrough in terms of fidelity. And what I mean by that is a kind of some reliable ability to get some reliance, and it's not going to break down as quickly, right? You get this decoherence happening. What are your views on that? Do you think that it's more in the longer term horizon, or you think in the next 10 years, or you think 20 years? I don't think you believe 2100 now, right?
Yeah, I mean, I think there's two separate issues. One is what problems will quantum really solve that we care about? That's one issue, because there are lots of things for which quantum will never be a replacement for conventional. In fact, the majority of things. The thing that quantum is really good at is if I have to simulate a quantum system. There is no better way to simulate a quantum system than with another quantum system. So that's where it really is. I think there are two challenges. There are really three, right? First of all, get as much stability and coherence as you can so it lasts as long as possible. Second, come up with a really efficient way to do error correction, because you're still going to have to do error correction. And the challenge right now is the overhead of error correction is way too high, much too high. So you have to build many more qubits than you really need. And the third is how much can you scale, and how can you scale? Clearly, the current designs, you're not going to be able to build very, very large numbers of qubits that are tightly interconnected in a single environment. simply because you can't keep the noise out of that system long enough. So we need to find ways to scale, and maybe, some people have proposed, there are different approaches, right? Because there are some people that are working on photonic-based quantum systems. They have different challenges than the super-cooled things that rely on Josephson junction structures. They have different challenges, but we'll see how the two play out. My guess in the next 5 years, one of two things will happen. One of these people will make a breakthrough and will really solve a really important problem. Not a problem, generating quantum random numbers is not an important problem, but solve a really important problem at reasonable scale. Or we're probably in it for the long haul. And the thing I'll say about quantum, Stephen, I think is very important, is it's going to force us to solve a really important set of hard problems. When there's a big breakthrough and how big that breakthrough is really hard to predict. But the problems you'll solve along the way, how to do sensing, how to do error correction, how to maintain noise immunity in systems, are things that silicon people are going to have to solve another 10 or 15 years down the road. So they're important problems, irrespective, and good problems in physics to be solved, irrespective of whether there's an immediate breakthrough in terms of quantum computers being really viable for large-scale applications.
So do you think that quantum, perhaps in a hybrid environment, combined with classical supercomputing, can solve certain issues? And you had NIST come out now with these two algorithms. I guess they're sort of being released in their kind of final form, or at least the framework for it, right? Or the ones that are applicable. Do you think that there's a whole idea of AP and MP? Do you think we're going to be to resolve some of these?
Yeah, well, certainly, I think if there's a viable system that's applicable to a range of applications, it's going to be that way. In the same way that you have a conventional CPU and you have a GPU as an accelerator on it, the same thing, right? So we'll have a conventional group of CPUs, and then we'll have a quantum unit that does the part of the application for which the quantum application is really good. I think we need a lot more people working on quantum algorithms. I mean, everybody still points to Shor's algorithm.
Right.
This is a discovery of many years ago. It's an important discovery. It's an important place where quantum demonstrates an ability to really do better. So now we need a list of hundreds and hundreds of other algorithms that have similar advantages.
Yeah, I mean, I saw this paper recently on photonics, and maybe it's a breakthrough in terms of kind of measurement-based quantum rather than gate-based, and maybe it can scale. I thought it was really, really interesting. Some of the topological stuff that's being worked on, I think that's interesting, right? Because then you can get the fidelity required. These are sort of kind of frontier research areas. So it'd be interesting to see what the applications. What are your thoughts on these frontier research areas?
Oh, I think there's a lot of interesting work. And I one of the things I found somewhat inspiring is people who think are spending time thinking about algorithms from a quantum perspective sometimes stumble on improvements in conventional algorithms, right? In much the same way that, IBM showed that some of these quantum computations and Microsoft, same thing, could be done on conventional computers just as well. But they were inspired by the way the quantum algorithm solved the problem rather than the conventional algorithm. So I think, this is going to be a time where the importance of algorithms and algorithm thinking and algorithmic efficiency becomes more important than ever. Because whether it's a slowdown in Moore's law or the shift to different computing models, which GPUs do, quantum does, that's really going to mean we need to rethink the way we do algorithms and the way the algorithms work in a way that's matched to a rather different kind of hardware structure.
So let's do a little bit of shifting here, because we talked about chip technology, supercomputers, quantum computing, we talked about AI, machine learning, but all of this is driving innovation in biomedical on the biomedical side, right? And the implications of that. Do you think that we're going to have a serious progress on aging? You have David Sinclair's, maybe some of the work is controversial at Harvard, but there's its Altos Labs with Yamanaka, the professor who got the Nobel Prize in 2012 for these 4 Yamanaka factors, maybe utilizing some of that in a kind of a de-aging rejuvenation program. Do you think that's going to appear in the next, let's say, 10 years, where we got meaningful progress in sort of the whole aging rejuvenation space, or do you think it's further out? Or
Well, I think we've made progress on a number of problems. I mean, I think if you look at what's happened over time as we've come through with various solution techniques, right? I mean, look at the reduction in mortality from heart attacks. That's been dramatic, right? And it's stents, it's statins, it's a whole bunch of some technologies as well as some meds that have reduced that effect, right? We're in most of the developed world, we're pretty good at handling infectious diseases. And in fact, if you look at what's happening, increasingly, people are dying of chronic diseases of old age, right? Cancer and neurodegenerative diseases. So I think in both cases, we need major breakthroughs, both on the diagnostic front and on the treatment front. If we could diagnose these things earlier, then we can begin to think about what the underlying scientific cause is and begin to think about what we could do to prevent Alzheimer's, right? Or Parkinson's or MS or any of these other diseases. Similarly with cancer, the really hard problem with cancer is figuring out, it's not finding, you might get an initial signal. The question is that initial signal, is it something you really should go after in some way or not? Because our own immune system is quite effective at taming very small tumors often, and there is no need for surgical intervention. So whether or not, I mean, there are some interesting things coming along there. Just recently, just the other day, a blood test was approved for looking for colon cancer, which is certainly a lot more pleasant than a colonoscopy as an alternative, and a lot more cost effective. A blood test is a lot more cost effective than going through what is effectively a surgical procedure, right, with an anesthesiologist and all. So I think things like that, figuring out how can we advance things, where's the opportunity to really make progress on these things. Not that we're going to live forever, but if we can create a situation where people have a steady plateau and they get to 100 in a healthy way, not needing significant medical care, that would be really a triumph.
yeah, and I guess there's so much existing data that you can apply some of these AI machine learning techniques to existing data to uncover things that are being missed, right?
Yeah, and if you can get a large enough database, the amount of data you need, for example, let's say to go after cancer or something else, is phenomenal. So getting that large database and getting accurate data is going to be the problem, and then while maintaining patient privacy and other things. But I think they're making progress, and I think the important, this tie between people on the clinical side and people on the basic science side is really crucial, because it's the people who are the basic scientists who understand the underlying disease mechanisms that are operating cancer or neurodegenerative disease. And it's the clinicians who actually see the patients and see the symptoms. So we need to get those two really collaborating tightly in order to get the kind of progress we need.
There's so much discovery and sort of on the boundary layers. And I've been following some researchers in quantum biology, but quantum biology is still controversial, right? But I think it's really interesting if you can get quantum effects and being able to have some kind of deterministic what's happening. Then you can get therapeutics or ways of doing diagnosis. And then, maybe photosynthesis has some kind of electron spin quantum element to it. Birds migrating in their sensing maybe has some kind of quantum elements to it. Do you think that's too far out, the sort of quantum in wet environments and being able to somehow quantify it and use it?
Yeah. I think the fascinating thing about science, as was said many years ago, it's an endless frontier. There is always new things to discover, and the product of the world we live in over this long period of evolution has built systems that work amazingly well. I mean, it is absolutely amazing how well, whether it's in birds knowing how to migrate over massive distances. What do you mean butterflies? Butterflies migrating over massive distances. I mean, it's really phenomenal. And so understanding what mechanisms are at play and taking them back to how this interrelates. And are there things, really deep things that these systems have evolved over time that we're not aware of? Quite possibly.
So I'm just doing a time check. We've been talking for an hour. Do you have a hard stop in like 7 minutes?
I'm getting close anyway.
Okay. So I'll start doing kind of the final round then of questioning. So we'll track. And I appreciate you extending to an hour. I mean, I could spend that afternoon with you on all of these different areas. And do you ever think about consciousness having some kind of quantum element? And this is more controversial. You know, you have Penrose's
original, yes, why AI would never work.
Yeah, but I've been tracking some of the papers out, and where there's maybe some like super radiance happening in the sheath, which seems to indicate some kind of quantum effect happening, right? Or some other research that says maybe there's an underlying theory where there's some quantum effects happening, or even outside of these aspects. Roger, because I did 3 keynotes with him.
Oh, wow.
So I had dinner with him, and I got to kind of mine kind of this thinking, or even this aspect of the universe, and it's really a continuum of bangs, right? It's not just one start and one finish. Do you have any thoughts on that work at all, or maybe you prefer not to comment because it's outlier, right? So.
It is an outlier. I think it's worth thinking about. I mean, the observation I'd make is, despite the incredible progress we've made with machine learning and these LLMs, if you look at how inefficient they are compared to the human brain.
Right.
I mean, we're off by 4, 5, 6 orders of magnitude in terms of the efficiency. So obviously the brain is able to do computation in a way that has some significant benefits over the way these artificial neural networks work, which are a crude approximation. They're not an exact model, right? We got analog versus digital. We have all kinds of things happening with frequency, and neurons are much more sophisticated than the artificial neurons, which are simple summation devices with cutoffs. So I think the real question is, and there are some people working on this critical issue of, can you get a better understanding of how cognition happens, how things like conscience happen, all these kinds of things by studying human brains? And then does that inspire you to think about changing the architecture of the way in which we do machine learning systems to really take advantage of that? And I think this area is just really beginning to open up as our understanding of how the brain operates at various levels, not just the single neuron firing level, but you've got billions of neurons there. They're all going firing, right? And how does that really work? We still don't really have as good an understanding as we need.
Yeah, or I've been reading some research where there's some computation happening even at the cellular level outside of neurons, right? So
yeah, sure. There's lots of in the optics system. There's lots of computation that happens before it gets to the brain.
Thank you, Ged.
Thank you, Stephen. Good to talk to you.
Thank you for listening to the brand called You Videocast and Podcast, a platform that brings you knowledge, experience, and wisdom of hundreds of successful individuals from around the world. Do visit our website www.tbcy.in to watch and listen to the stories of many more individuals. You can also follow us on YouTube, Facebook, Instagram, and Twitter. Just search for the brand called you.